Welcome back to another deep dive. Today, we are tackling a topic that often sits on the scary list for network engineers.
It definitely can be.
Not because the concepts are impossible, but because the acronyms alone are just enough to make your head spin. We are looking at the Juniper JN0-650 exam.
The enterprise routing and switching professional track, to be specific. Yeah, it's a beast of a track. It covers a lot of ground.
It really is. And before you tune out thinking, oh, I'm not taking a test today, just hold on. Because as we went through the source material, the practice questions, the docs, we realized something. This isn't just about a certification. It's really a roadmap for how modern professional-grade networks actually function.
That is exactly the right way to frame it. It's so easy to look at a syllabus like this and just see a list of, check boxes.
Do I know OSPF?
Yes.
Check.
Do I know BGP? Check.
But if you step back, what Juniper's really asking here is, do you get how to build a network that doesn't just pass traffic, but does it intelligently? Right, it's moving beyond the did the light turn green when I plugged the cable in phase.
Precisely. We're talking about next-level networking here.
Yeah.
The material goes from the backbone protocols that move data across continents, like BGP, to the really cutting-edge data center stuff like EVPN.
It's a huge range.
It is. It's the difference between, say, laying down asphalt for a road and designing a smart highway system that manages traffic flow and reroutes cars automatically.
And to make this digestible, because there is a massive amount of ground to cover, we're taking a specific approach today.
Oh.
We have a stack of specific practice questions from the exam material. But we aren't just going to, read the answer key. We're going to use them as case studies.
I love that. Use them to unpack the why.
Exactly. The engineering logic behind the answer.
It's one thing to memorize that option C is correct. It's another to understand the specific engineering pain point that option C solves in a real network. That's where the learning is.
So let's start at the foundation, the backbone. We have to talk about routing protocols. And the first one that jumped out was a scenario with OSPF.
Open shortest path first, yep.
And the setup in the question is something you see everywhere now, mixed link speeds.
Sure, you've got your older 10 gig links and then you've just installed some shiny new 40 gig pipes. Very common.
So here's the problem. The question asks, you want to ensure the shortest path calculation accurately reflects interface bandwidths. Which parameter should you adjust globally? And the answer was reference bandwidth.
This is a classic math problem that catches so many engineers because they trust the defaults way too much.
So what's the math?
Okay, here's the deal. OSPF calculates the cost of a link using a very simple formula. It takes a reference bandwidth number and divides it by the actual interface bandwidth.
Okay, reference divided by actual speed. Seems simple.
It is. But that default reference bandwidth was historically set to 100 megabits per second.
100 megs? That's not very fast today.
Not at all. But back then it was. So a 100 meg link had a cost of 1. But here's the kicker. OSPF doesn't really do fractions. It floors the result at 1.
Oh, I think I see where this is going.
Yep. If your reference is 100 meg, then a 1 gig link gets a cost of 1. A 10 gig link gets a cost of 1. And that brand new 40 gig link.
Also a cost of 1. So the router thinks a 40-lane highway is the same as a small road.
To the router, they are identical. So OSPF says, hey, these paths are equal cost, and it starts load balancing. Or even worse, it picks the 10 gig link for some other arbitrary reason.
And your expensive 40 gig pipe is just sitting there underutilized.
Exactly. It's a disaster. So the fix isn't touching the interface itself. It's changing the ruler you measure with.
You have to adjust that reference bandwidth globally.
You set it way higher, like 100 gigs or more. Suddenly the math works again. The 40 gig link gets a much lower cost than the 10 gig link, and OSPF says, oh, that's the fast pass.
It's such a critical detail. One of those things that if you forget to set it, your network efficiency is just, it's tanked from day one.
And that's why it's on the exam. It tests if you understand the why, not just the command.
Okay, let's level up to the big boss of routing. BGP, Border Gateway Protocol.
Ah, yes.
Now, BGP is famous for being complex, but the source material had a question about its decision-making process, specifically in Junos OS. It asked for the first tiebreaker.
BGP is notorious for this. It's like a pilot's pre-flight check with this huge list of attributes it checks in a specific order.
And the options were things like AS path length, origin, MED. But the answer for Junos was local preference. Why that one? Why does it get top billing?
This is so important because the order really matters, and it can vary a bit between vendors. But in Junos, Local preference is king. It's the first attribute checked after, making sure the next hop is reachable.
And the reason it's first is?
Policy. It's all about policy.
What do you mean by that?
Local preference is an attribute you use inside your own network, your autonomous system, to decide how traffic leaves your network. It's you telling all your routers, hey, I don't care what the rest of the world thinks, we prefer this exit door.
So it's about control. Before you even look at how long the path is, you look at what your internal policy dictates.
Precisely. It gives you deterministic control. Think of it this way. You might have a shorter path through ISPA, but maybe they charge you 10 times as much per gigabyte as ISPB.
Right. You don't want the router just picking the expensive path because it's one hop shorter.
Of course not. So you use local preference, you set a higher value for the path through the cheaper ISP, and you force the traffic that way. It overrides the natural behavior to enforce your business logic.
It's the home court advantage rule. Okay, sticking with BGP, there's another question that I think trips people up. Internal BGP, or IBGP, and something called next hop self.
The reachability puzzle. This is a stumbling block for almost everyone learning BGP.
The question's answer was, to ensure that external routes are reachable by internal peers. Can you break that down? Why wouldn't they be reachable?
Okay, imagine you and I are routers. I'm on the edge of our network talking to the internet.
Okay.
I learned a route to Google from an external router at our ISP. The next hop for that route is the ISP router's IP address. Let's just say it's 5.5.5.5.
Got it. So you know how to get to Google. You send the traffic to 5.5.5.5.
Right. Now, I turn around and I tell you, my internal buddy sitting deep inside our network, about this route. By default, with IBGP, I don't change that next hop attribute. I pass it to you as is.
So you tell me, to get to Google, go to 5.5.5.5.
Yep. But you're inside the network. You don't have a direct connection to the ISP. You have no idea who 5.5.5.5 is.
My routing table is empty for that, so I just drop it.
You drop it, you mark the route as invalid because you can't reach the next hop. So you essentially ignore the route to Google. It's a black hole.
The map is useless if you can't find the entrance to the highway.
Perfectly put. Next hop self fixes this. When I advertise the route to you, I change the next hop to myself. My own internal IP.
Ah, so you know how to reach me.
You do. And I'm basically saying, to get to Google, just send the traffic to me, I'll handle the rest. It ensures the path actually resolves inside our network.
It's the I got this command.
I might have to steal that. The I got this command. I like it.
You can have it. All right, let's shift from routing to switching, the plumbing of the local network, and we have to talk about spanning tree.
The protocol everyone just loves to hate.
Seriously.
Yeah.
The practice question highlighted this really specific problem. It said, you want to prevent a single broadcast domain from becoming too large, but you also want to save CPU resources.
The classic trade-off.
Right. Because running a separate spanning tree instance for every single VLAN just kills your CPU.
It's the old way, like PVST per VLAN spanning tree. It gives you great control because every VLAN has its own loop-free topology. But if you have 500 VLANs...
You're running 500 instances of the protocol.
And every single one is sending hellos, doing calculations. It crushes the CPU. If the network flaps, your switch might just spike to 100%, trying to recalculate 500 different trees.
So what's the Goldilocks solution? The source material points to MSTP, Multiple Spanning Tree Protocol.
MSTP is the elegant middle ground. Instead of one tree for everyone, which is bad for traffic flow, or one tree per VLAN, which is bad for the CPU.
You group them.
You group them. You map multiple VLANs to a single tree instance. You could say VLANs 1 through 100, they all basically follow the same physical path, so let's put them in instance 1.
And now the switch is only calculating for a few instances, not hundreds?
Exactly. You slash the control plane overhead while still keeping the network loop free and allowing for some load balancing. It's all about scalability.
Speaking of scalability, we have to talk about the future, or I guess the present in the data center. EVPN VXLAN.
The scary acronyms.
The scariest. The practice question asks about the tech used to encapsulate Layer 2 frames into Layer 3 UDP packets. The answer is VXLAN. But then where does EVPN fit in?
You have to think of them as two separate jobs. VXLAN is the shipping truck. Its only job is transport. It takes your Ethernet frame and wraps it inside a UDP packet so it can travel over a normal IP network.
So it's the vehicle. It lets us stretch Layer 2 across a Layer 3 network, but why UDP?
That's a great question. By using UDP, you get a source port number that you can hash on. This allows the underlying network to load balance the traffic across multiple links using standard methods.
Ah, clever. So VXLAN is the truck, but a truck needs a driver, needs to know where to go.
That's EVPN. EVPN is the control plane. In the old days, a switch would just flood traffic everywhere. Hey, are you Bob? Are you Bob? It's so noisy.
And EasyPN stops that.
Completely. EVPN uses BGP, our old friend, to actually advertise MU addresses. The switches talk to each other and say, hey, I have Bob connected to me. If you have mail for Bob, send it directly to my IP address.
So it's basically a routing protocol for MAC addresses. It eliminates flooding.
Exactly. The analogy in our notes was perfect. VXLAN is putting a letter inside a bigger shipping box. EVPN is the address label and the entire Postal Service logistics system that gets it there efficiently.
That creates a much quieter, more stable network fabric. Okay, one more on switching. Private VLANs, specifically the isolated VLAN.
Great feature for shared environments, hotels, universities.
The question asks which type of VLAN allows ports to communicate only with the promiscuous port.
The terminology is always a bit funny, isn't it? The promiscuous port is just your gateway, your router. And the answer is an isolated VLAN.
So if I'm in a hotel and I'm in an isolated VLAN and you're in the room next door also in that same VLAN,
Yep.
we can't talk to each other.
Nope. You can't ping each other, can't see each other's file shares. The switch enforces a rule at the hardware level. No talking to your neighbor.
Okay.
You can only talk to the gateway to get to the internet.
It's social distancing for switch ports.
That is a perfect way to put it.
All right, let's move to our last topic. Quality, control, and access. This is where the network starts getting smart about what's inside the packets.
Right. Not all packets are created equal. A YouTube video buffering is annoying. A voice call dropping packets is unusable.
First up, class of service, or COS. The question was about a component that assigns incoming packets to a forwarding class based on existing headers. The answer is the behavior aggregate classifier. That's a mouthful.
It is, but the concept is actually about efficiency. Think of a post office. A letter arrives that already has a priority mail stamp on it.
Okay, that stamp is like the DSCP value in the IP header.
Exactly. The behavior aggregate classifier is a postal worker who just looks at that stamp. He doesn't open the letter. He just sees the stamp and says, priority, this goes in the fast bin.
So it trusts the marking that's already there.
You trust the stamp. It aggregates that traffic into a specific behavior, like expedited forwarding. It's incredibly fast because it's just looking at a header.
And that leads right into VoIP, because voice traffic needs that priority stamp. But nobody wants to manually configure every desk phone.
Oh, that's a nightmare. I've been there. Never again. That's why the exam covers LLDP-MED.
Another acronym soup, Link Layer Discovery Protocol Media Endpoint Discovery.
It's basically a negotiation. You plug the phone in, it sends a packet saying, hi, I'm a media endpoint. The switch hears this and replies, welcome, please send all your voice traffic on VLAN 50 and tag it with this priority.
And the phone just configures itself. No manual work needed.
It's automation at the access layer. A lifesaver.
Now, what about Multicast? A company-wide video stream. How does a router know a computer wants to watch it?
That is the job of IGMP Internet Group Management Protocol.
Not to be confused with ICMP, which is ping.
Right. Totally different. IGMP is the signal from the host to the router. Your computer sends an IGMP report that says, hey, sign me up for this group.
It's a subscription request.
It is. Without it, the router would just drop the multicast traffic.
Right.
IGMP is the sign me up button that tells the router to start forwarding that stream.
And finally, we have to secure all of this. 802.1x, the gold standard for port authentication.
This is about knowing who or what is plugging into your wall jack.
The question focused on the authenticator. It asked which component acts as the proxy.
In 802.1x, you have three players. The supplicant, that's your laptop. The authentication server, that's the Radius server with the password database.
And the authenticator is the switch.
Correct. The switch is the middleman. You plug in, the switch blocks the port, you send your credentials. The switch doesn't know your password, so it just packages up your info and proxies it over to the Radius server.
It just mediates the conversation.
It does. The server says yes or no, and the switch, the authenticator, enforces that decision by either opening the port or keeping it blocked.
Thank you for diving deep with us today into the world of Juniper routing and switching.
Keep learning and keep questioning those defaults.
See you on the next deep dive.